All right. Well, then we're going to get started. All right, we are on, I think it's section 4.4. Yes, mean value theorem. And the mean value theorem gives you a really interesting tool to work with. But you have to start off with something a little bit simpler first. And the book starts off with something whose name is something French that I've never been sure how to pronounce. I don't know. I don't understand French at all. Raleigh, I don't know how his name. Let's say Raleigh. Raleigh's theorem. Okay? I don't know exactly. But what Raleigh's theorem says is, suppose you've got some function. And it's differentiable. That means like we can take the derivative of it. It doesn't have weird corners and things like that, or gaps in it, or any of the kinds of things that cause trouble for differentiation. But you know, like it's a polynomial, or it's trig functions or something. And let's say there's some range, I'll call it I, some interval, where the beginning of that function over that interval and the end of that function over that interval are equal to each other. It starts and it ends that range at the same value. In other words, like if this is A and this is B, then f of A equals f of B. Okay. I mean, you could almost always come up with something like that. Okay? I mean, given a parabola or something like that, we could come up with ranges that would work like that. And what Raleigh's theorem says is, there will be some place inside of that range where the derivative is 0. In other words, there will be some place between there and there, between between A and B, there'll be some place along the way here where the derivative is equal to 0. In other words, the slope of the tangent line was 0. Which at first sounds kind of astonishing, and then you think about it, and it makes really good sense, right? I mean, you can't really think of how you could possibly draw this where it wouldn't be that way. I mean, I'm going to try to draw some kind of function. No, I won't. I need a pen. There it is. I mean, no matter what I tried to draw, if I'm connecting from one place to another that are at the same, height, no matter what I do in between here, there's got to be at least one place where the slope is 0. If you actually go on Wikipedia and check, this is a theorem from like 1691. Calc was invented in like 1680. Okay, so this is one of the very first things we figured out about calc, was that this had to work. Was that as long as you have a range where it's differentiable along, you can see how this wouldn't have worked if like there were corners and gaps and all that kind of crap. But if there wasn't, this would work. As long as you know that the beginning and the end of the range at the same value, as the function goes through there, there's going to be at least one place where the derivative has to be 0. In and of itself, I don't know that there's that many applications of Raleigh's theorem or whatever, other than as a way to kind of give it's sort of the gateway drug to get us over to where we're going with this, which is the mean value theorem. Because Raleigh's theorem turns out to just be a special case of the mean value theorem. It's just one specific example of how it could work. This business of we started off and ended at the same the same place on the y-axis, well, that's awfully specific. It doesn't seem like it would have to be that way, and it turns out it doesn't, because we could have the mean value theorem. Let me draw another set of axes here. And we're going to draw some function coming through here. Oh, I don't know, maybe something like that. Okay. Forget about they have to start and end at the same place. I'm going to say, here's some range. Here's like A. Here's B. This is our range I. is the interval we care about. As long as the range of the function across that range is differentiable, there's no nonsense, can be differentiated, there's no nonsense of gaps or anything like that, we have an interesting possibility here. If we took where we were at the beginning and where we were at the end, there is some little line that connects them. Hey, we had that line back when we first were learning about taking the derivatives. You might even remember it. That was called a secant line. Where that secant line was just the straight line that connected two places on the function. The mean value theorem tells us something interesting about this line. It says someplace in this range, there'll be a place where the derivative at that place, its tangent line, has the same slope as the secant line. In other words, there's at least one place along the way where the tangent line and the secant line are parallel to each other. Let's find a way to write that. I mean, the slope of that secant line would be, let's see, rise over run, how we write slopes. So let's see, the rise would be the difference between f of b and f of a, divided by the difference between b and a. But the mean value theorem says that there's definitely some place C, maybe more than one such place along the way, where f prime of C was equal to the same thing. In other words, there will be some place where f prime of C is equal to this. We don't know yet where it is, but there will be such a place. And again, if you kind of started playing with it, tried to figure out how you sketch it, no matter how we did it, you could start seeing, hey, there's got to be places like this along the way. Because as our line goes from as our function goes from A to B, there's going to be times where it was more sloped, and times when it was less, where it was more sloped, and times where it was less, and somewhere along the way it will have been the same slope as the secant line. Your book goes through all the trouble to prove this one. And then never asks a question about it. Therefore, I don't care. Okay? The proof isn't what's interesting and important about the mean value theorem. This is an interesting rule, except why are we calling it mean value theorem? Let's see if we can figure out why we would call this the mean value theorem. Let's make a new problem. Let's make this axis here time, and this axis here is height. I'll use z for height. And we're talking about like what's something that we would have changes in height? We're dropping a ball. Okay, we're dropping a ball from some height above the ground. Where is the ball at any given time? So like at some time we started, the ball was right here. At first it's falling slowly, and then it falls faster and faster. So we have some function, f of t, that describes how high the ball is at any given time. Maybe it's 100 minus t squared. This is our function that describes where the ball is. You know, z is the height of the ball at any given time t. The ball is not moving at all at the beginning when we let it go, but gravity accelerates the ball. There is some time, in fact, it's going fastest right when it hits the ground, right? Maybe that isn't drawing very well here, but pretty close. Okay? At any given time along the way, like at this time right here, I'll call that t1, at that time t, the derivative of our function is the speed of the ball. What is the average speed of the ball? What was its average speed? Well, this isn't really all that hard to figure out. We know how far the ball went. This was at 100 at time t equals 0. It was at height 0 at the end. So we know it went 100 meters, or whatever our units are, in a certain amount of time, from t equals 0 to t equals, well, it's going to be t equals 10, actually. It's going to have taken 10 seconds to fall. So we will have fallen 100 meters in 10 seconds, or 10 meters per second. That is this slope. This slope is 10 meters per second. At the beginning, we're going much slower than that. At the end, we're going much faster than that. Someplace along the way, though, according to the mean value theorem, there's a place where we're going the same speed of that. This is its average speed, its mean speed, but there is some place along the way where our tangent line is parallel to this, where we're going the same speed as the average speed. At first the ball was going much slower than 10 meters per second. At the end it was going much faster than 10 meters per second. Your book spends like 2 pages proving, therefore there must be some time along the way where it was 10 meters per second. Alright? So what we now know is, we know that there is some time, here, we'll call it t, what should we call this time? I don't know. T naught, t0. There'll be some time where the derivative at that time is this mean value. So let's see, what is the derivative of f prime of t? Well, it appears to be negative 2t. And we know that that will be some time, that negative 2t will happen, there is some time where it's equal to 10. Therefore, that is at t equals negative, I have the sign wrong. This is a negative 10. This is a negative 100, so that's a negative, whatever. We'd have to keep the sign straight on all of this. It was negative because they were going closer to the x, downward on the graph, closer to the x-axis. So there was some time, apparently at t equals 5, where the ball was actually moving at the mean speed. Before that it was going slower, after that it's going faster. And that's it. Proving this thing's a mess. Now, on the actual homework set, a lot of the problems are more about, like, when could you use this? Like, it's having you, what is the range of values on this function we could do this? Because remember, we have to be able to differentiate the function. So if you have something going on, like f of x equals 1 over x, well, there's a problem when x equals 0, right? You could do this for anything other than 0. So you'll have to look at the back of the book at what notation they want. Something like from negative infinity to 0, or from 0 to positive infinity, this would work. So some of the problems are just kind of figuring out what range this would work. Some of the problems, it says sketch the graph. No, it says use a graphing calculator to sketch the graph. What are you going to do? What's your favorite way to make a sketch of the graph and then transfer it to paper? Like, I seem to remember last year everybody loved Desmos.com or whatever. Would that be a way that you guys would be happy doing it? Okay. Desmos.com, WolframAlpha.com would all be fine ways of doing it if you don't love your graphing calculator. Okay, I'm not in the business of teaching people how to run all their different graphing calculators. But no matter what, there's going to be problems in this section where it gives you some fairly messy looking equation, and they say sketch a graph of it, but they don't mean like as in literally come up with a table of little values and try to plot them yourself. They mean use like your graphing calculator or something, make a plot of it, and then transfer it to your paper. Okay, because what they want you to do let's say your function ends up looking like this. And they're going to say, over this range right here, where are the places where, according to Raleigh's theorem, the slope is going to be 0? Well, they kind of want you to use this graph to help you see, oh, once I did this, I set the derivative of this function equal to 0, and I solved for two values of x. They want you to be able to label them on your graph and so on. Okay? They don't want you to go to all the work of coming up with a graph from scratch. They want you to transfer it from a graphing application or whatever. Okay, so doing this stuff is not conceptually all that hard. I was glad that this landed on the one right going into spring break. I think everybody's going to be okay with this one. Alright, let me get the assignment. If I remember right, part of the issue here is the assignment is pretty small. That was also something that made me glad it was the one that went into spring break. Wait a minute. Nope, there it is. Wait. Yeah, okay, so we're on page 388 in your book. And the assignment is actually 153 to 159 odd, which is not very many problems, plus 185 to 198 odd. 185 to 198 odd. So I mean, gosh, that's only like 4 problems, and that's like 6 or something. I mean, there's not that many problems to do here. It turned out a lot of the problems that give you in that assignment that I didn't assign you were more like, explain why. Well, I don't feel like getting in the business of like trying to grade your explain type answers. Okay? I don't like asking that on a test or anything like that. Alright, well that's all we needed, and we'll work on that, and I will turn off the recorder.